Hello everyone, my name is Saman Zaltutaj. I'm a researcher at Quality and Usability Lab, and I'm going to present a work on quality estimation models for gaming video streaming services. This work has been done in collaboration with colleagues from Norway, from University of Oslo and Simula Research Lab, and my colleagues from TU Berlin. So I will start with motivation and backgrounds of the work. So when we are talking about cloud gaming service, we already know that cloud gaming is a delay-sensitive application. And because of this delay-sensitive application, we have to deal with a very new concept and lots of differences compared to the traditional video streaming services that we have seen. So, for example, NVIDIA using GPU hardware accelerator engines for encoding the videos in order to do it quite fast, which has a quite different preset compared to the traditional video streaming or video encoding setting. I have seen some companies using fixed multiplex size for fast encoding, short group of picture, or infinitive group of picture. Most of the cases we don't have any B-frame, for example. So these changes making the video streaming to be quite different. And when it comes to the content, also it's quite a special type of content that we are dealing with. It's a rule-based system with a special characteristics. We have a pool of these pre-designed objects that will be repeated again and again. We have a certain levels of abstraction in each game, and which is coming from the design concept of the game. And we have typically a special motion pattern. So, which is, for example, in racing game, we already know how the motion would look like actually. I made a short comparison between accelerator engines and let's say that typical or software packages that we have. So NVIDIA provided the accelerator engine for HEVC and H.264, and here you can see the comparison between LLHQ preset of such accelerator engines using NVENC and to medium and ultra fast preset. So we compared it for one video sequence at 1080p resolution, and as you can see for bitrate, whenever it's lower than 2 Mbps, the result showing that there is a huge difference, especially in H.264. So that LLHQ actually works quite well, and whenever it's higher than 2 Mbps, so the medium preset is quite similar to LLHQ. So the next point is that we need to have access to the gaming video dataset. So unfortunately, I cannot explain all this dataset here, but we have found only 3 gaming video dataset. Which was not enough to make any proper, video quality model for gaming content. So we decided to make a new gaming dataset, gaming video quality dataset, which we use different resolution, multiple bit rates, and different frame rates, and using LLHQ or low latency, high quality preset using NVIDIA encoder or accelerator engine using H.264 compression standard. And we build a really huge data set conducting 4 different subjective tests and using anchor condition to come up with this data set. And we had over 150 participants who were participating in this test actually. So another difference that we have in this data set compared to previous data set is that we, in addition to video quality, we also ask for fragmentation, which is more similar to blockiness. Then we ask for unclearness, which is similar to blurriness, so which the concept is blurriness, and discontinuity is when we have a low frame rate and there is a interruption in the flow of the video or stuttering in the video. So you can see here the bar plots for 1080p resolution of all games that we have used in 3 bitrates. So we have more bitrates per resolution, but we show them only a few of them, but you can read that here. As you can see for 2 Mbps, we can see that there is a nice increase of the let's say that the quality ratings, and that is coming from the fact that the video that we selected, they have really different complexity levels, and they cover nice range of complexity of videos, and it was we decided to make it like that. Unfortunately, the dataset covers proper range of the video games in different levels of complexity. So in terms of the scale, so we use 7-point continuous scale, which was proposed and used in P.809, which is a subjective recommendation on subjective quality assessment for gaming quality assessment. And as you can see, that's quite different from traditional traditional video quality assessment that we have ACR scale. So next we investigate the performance of existing video quality metrics. To do that, we use the classification that was proposed by Professor Roque from TV model, and you can see different types of, let's say that models, planning, Bitstream, a signal-based model. You can have a look through the paper to see the differences between them. So, which we don't have enough time here to explain that, unfortunately. With respect to signal-based model, so we selected 4 different but famous and quite renowned food reference metrics, and in order to report the results, we use Pearson correlation and Spearman correlation for all frame rate, and once only for 60 frame rate. And the point is that if we have all this frame rate, because there's a video discontinuity, there is a lower frame rate which cannot be captured by image quality metrics such as PSNR or SSIM, it will be maybe the result is misleading. So that's the reason that we decided to also have 60 frames per second separately. So for VMAP, we can see the result is quite good, which was expected. We also have seen in previous work that VMAP works quite well with different types of content. So with no reference metric, we selected 3 famous no reference metrics, peak and nick, which we did not retrain them again because with gaming content, because actually we don't have such a data set that we can retrain them. So we don't have an image gaming data set to retrain these models actually. So the result is not good, so which was expected. We also have seen in our previous work that these metrics, they don't work unless you retrain them again. And we also have 2 other models like NRGBQM, which is a gaming, both of them are gaming models, and they are actually trained based on gaming content. The first one trying to predict the VMAP, and second one is a deep learning model, which sadly it's not yet published, but you can find a slide and information about that on VCorg. I presented once, and also you can find it on my GitHub page, the source code for that. So NDNet Gaming is a deep learning based model based on dense architecture, which is trained based on the gaming content actually, and performs quite well. So in terms of the Bitstream and opinion models, we decided to compare or actually investigate the 3 recommendation, 2 opinion model, G.1071 and 72, one for streaming video and audio streaming application, the second one about cloud gaming services, and the third one, which is a Bitstream model, and which is developed for adaptive streaming actually. As you can see here as a result, so G.1072 leads G.1071. So in general, G.1072 using the same equation as G.1071 with a small difference that it is retrained based on gaming content. So P1203 also, we can see the result here, and it worked quite well. So mode 0 is similar to opinion model, and mode 1 using, let's say that Bitstream information from the header information such as iframe and pframe size was used here, and mode 3 can have access to more information such as quantization parameters as well, which actually performs very good, as you can also compare it even to VMAP as a signal-based model. It's really actually a good result that we can see here. So in terms of proposed planning and monitoring models, we first start with data preparation. As I explained before, we had extended continuous 7-point scale that we used, so that's why we decided to transform that back to ACR scale to be, in line with other works, and then which we use the equation that you can see here. You can also see the paper how we did that. Then we normalize the most values, and then we calculate the R values using the recommendation from eModel. So what they have done there, we repeat the same thing, and then finally we calculate the impairment. So that means that for each impairment that we have, such as video discontinuity, video, let's say that unclearness and fragmentation, we had 1 impairment that we could have, use that for modeling or, for modeling purpose. So regarding the planning model, so we decided to predict the impairments of the video discontinuity only based on the frame rate, which is, as you can see, based on the exponential function. And then we had the impairments of the video fragmentation as similar to other works, for example, from G.1071. We calculated bit per pixel, and then we use a logarithmic function to predict this impairments. And then finally, We may predict the video uncleanness based on the scale ratio, which video uncleanness is blurriness, which coming from the upscaling artifacts. So that's the main reason that we made this metric, or let's say not metric, but parameters we added also to our model. For monitoring model, for Bitstream model, what we tried to do, we wanted to have more data because we wanted to use machine learning to train that. We had 30-second video sequence. We decided to take 5-second duration intervals, or intervals, short intervals that we, let's say, that have more data. So we split them in 5 seconds, and if you have these 5 seconds for each video, we can get 6 different, let's say, the chunks, and then you can increase your data set 6 times more. The problem is that you have the most value on the whole 30-second and not on 5-second duration. So that's why we try to calculate the weight of each frame. So how much contribution one frame has based on NVNet gaming model, so which was a deep learning model, which is trained based on gaming content. And that's actually telling you the weight and contribution of each frame. And if you know that, then you can actually calculate the MOS for each, let's say, that short intervals or that we have, and using this weighting. So I need to mention that we neglect the recency effect that could happen, but I hope that with 30 seconds we don't have such an effect. So for monitoring model, we use a short interval. But we calculated extracted several features: frame rate, scale ratio, average, bit rate of 5 seconds, but also number of iframes, statistics about iframe, p frames, and then video complexity. So with all this information that you can actually read from the header of the packet, we made a factor analysis, and then we try to find out which of those factors or parameters would play a role, and we only selected those that play a role for one impairments, and then remove the rest of them, and to make our model less complex. And finally, we use random forest, so 3 different random forest models to predict each impairments, and finally put them together to make a prediction of overall QE. So to do that, we use the core perceptual video quality model. So this is inspired by E-model, so which we have a R max, which here is 100 minus all these impairments that we have. So for opinion model, our fit is actually, we can see it here, and as is quite obvious, video discontinuity has a very small coefficients, so this contribution is not that high, which is coming from the fact that 30 frames per second and 60 frames per second, there is not a huge difference between them, and most of the changes is coming from 20 frames per second, which is not dominant here. So, and R max is 100 here, and for Bitstream model also we have quite similar, let's say that equation, only with some minor changes in coefficients, but which is coming from the fact that Bitstream model can make better prediction. So as a result, as you can see here, the opinion model in the training set works really good, performs very good, and the test set also it's okay, acceptable. You need to keep in mind this classification of the videos is super important, make it so difficult to make a very good opinion model for any video streaming application. When it comes to Bitstream model, the result is way more convincing. So we have really high Pearson correlation and Spearman correlation, but do not compare it with the previous result that we had for other metrics, because here it's only based on a small set of data set. So based on only, I think, 4 or 5 source videos that we have multiple encoding setting of that, which is not comparable to that. Here also you can see the scatter plot of that. And next we will just conclude this paper. First of all, you can find the implementation code on my GitHub. So it's very important to talk about the video complexity, especially for planning models, for opinion models. So you cannot come up with a good model without considering the complexity of the games. And next is that passive interactive test. There is also discussion in the paper. You can have a look why we use a passive test and if we can replace that or not. We start a new work item in ITU, which is about Bitstream model for cloud gaming services, and feel free to join us and contact me if you would like to join as a collaborative work and royalty-free model that we are going to develop. And if you want to update this model and use that for different cloud gaming services, you most probably need to update video fragmentation for sure, but maybe the rest of the let's say that the model, if this video encoder is quite different, or there are some changes that is happening from one cloud gaming service to another one. Thank you very much. feel free to contact me or send me any email if you have. So you can find my email address here.